Hello. Welcome, everyone. I'm Josh Tenenbaum. Thanks for coming in on a weekend to this exciting event. We have really fun talks and hopefully interactive discussions, just really talking about how we can move the field forward in understanding general intelligence, and especially excited to draw on the perspectives of cognitive scientists together with AI researchers in academia and industry and the nonprofit world. Greg here is the head president, I think, of the ARC Foundation, which runs the ARC-AGI prizes. We'll also hear from Mike Knoop and Francois Cholet, who have also co-founded the ARC Prize, and they have a company lab, NDIA, that is working on AGI around these things. And a bunch of our MIT faculty, students, postdocs, one alum, and anyway, it's a really exciting day. So hand it over to you guys.
Wonderful. Thank you very much, Josh. I first want to start off and say thank you, Josh, and the Department of Brain and Cognitive Sciences for hosting the ARC Prize Foundation today, specifically Praful, Katie, and Lance for helping organize for today. So like Josh said, my name is Greg Kamradt, president of ARC Prize, and today we are going to be talking about what it means in the ARC Prize way to be interpreting whether or not AI models are getting smarter or not. So in the next 20 minutes, I'm going to show you why interactivity gives us a new tool to measure model intelligence. I'm going to demo for you ARC-AGI-3, which is our new interactive benchmark. And what's really cool, and this is actually very special to this talk, is we're going to deep dive into action efficiency as a proxy for learning efficiency and intelligence. And the way I like to start off is there's no doubt that AI models are making progress, but there's an open question, which is, well, what are they making progress towards? Now, if you measure frontier model performance in a narrow skill, in a narrow domain, and that's your target metric, then you're going to be making progress in a narrow domain. However, if you want to make models that are generalizing, then your metric needs to be ability to generalize, or simply narrow target, narrow progress. And the first point to do this, if you want to measure generalization, well, you need to define what it means to be intelligent. Now, in 2019, Francois Cholet came out with his paper on the measure of intelligence, and he proposed a definition of intelligence in just 3 words, which was skill, acquisition, efficiency. Or put another way, how quickly can you learn new things? Now, we already know that AI can get good at any one single thing, whether it be chess, whether it be Go, or whether it be self-driving a car. There's a well-worn path to making AI good in a narrow domain. But getting those systems to learn something new, well, that part is still out of reach. Now, using this opinionated definition of intelligence, Francois Cholet started the ARC Prize Foundation with Mike Knoop in 2024. So ARC Prize Foundation is a nonprofit with the mission of acting as a North Star towards open AGI. And we define AGI as a machine's ability to learn as efficiently as humans. So as an organization, we build benchmarks that test the intelligence of machines by specifically measuring their ability to generalize. Last year, we were invited by OpenAI to join them on their live stream to co-announce the results of their O3 preview model. This was December of last year on ARC-AGI-1. This is our first benchmark. But looking forward, it's in my view that once we do actually have AGI, and once it is human-like, it's going to show up as interactive. And it'll be seen what looks like agents that are learning and adapting on the fly. And the reason for that is because intelligence is inherently interactive. The real world isn't giving you one-shot problems. Intelligence is going to unfold step by step through perception, feedback, and ultimately action. And so if intelligence is interactive, well, then we need new ways to evaluate this behavior. And we're already starting to see early signs of this. Here's a view of GPT-5 playing Pokemon. They actually have a live Twitch stream that shows you this whole thing. It may look like a toy example, but there's actually a lot going on underneath the hood here. This person who made this harness for Pokemon, they're trying to test whether or not the agent can make long-term plans, whether it can explore the environment, tackle short-term meta goals, and see how they do on long-horizon tasks. So what this is showing us is that if you want to measure interactive intelligence, well then you need interactive benchmarks. Static benchmarks, the ones where you just ask questions and then you get answers back, they're not going to do it for you. And we get a lot of new things with interactive benchmarks. You can test an agent's ability to explore the whole perception, planning, and action loop, as well as memory, goal acquisition, and what's very cool is you can start to measure alignment and cooperation within agents as well. And again, this is just something that you're not going to get with static benchmarks. So What ARC-Prize is doing is we're creating ARC-AGI-3. We're combining all of these core ideas into a series of over 150 novel environments. You can think of these as video games, and we are creating these ourselves. In fact, we built up a mini game studio just to make this happen. If anybody's curious about this, we have our lead game developer, Hunter, down here in the bottom left. He can talk games all day long. The whole goal with ARC-AGI-3 is we want to test the test taker's ability, and the test taker being, in this case, either human or AI. We want to test their ability to adapt to novel environments in order to not only complete goals, but we want to see, can they figure out what the goals are in the first place? So each one of the ARC-AGI-3 games will be built entirely on new game mechanics. So each one of these games is going to be as different from each other as Connect 4 is from Pac-Man is from chess. Now, we won't literally make those games, but that's how variety some of the game mechanics will be. And each one of the game designs is extremely intentional. Back to Francois's definition of intelligence, we want to measure whether or not the person taking this test can adapt to new situations, meaning we don't want to test just one single type of game, or else they would just be learning once and then repeating that skill that they have. The games will be split across a public and private test set. Public games researchers will get used to, but all performance scores, when we go and actually measure AI, that will be done on the private evaluation set. And it's private because the developer nor the AI will have ever seen these games beforehand, and therefore we can claim that they are truly generalizing to these unknown environments. What I'd love to do now is, because this is such a visual example, let's look actually at a demo. So here we have our first game, and when you first look at the screen and it's not moving, it's kind of hard to tell what's going on, right? And that's actually kind of the point here, because what we want you to do is we want you to start to click around and start to see what different actions do. And so now you can start to see, oh, I see I'm controlling some sort of character and I need to figure out what's going on. Let me go up to the black square up at the top. That doesn't do anything. Let me go down here. Oh, interesting. Something in the bottom left just changed. And now as you're clicking around, let's try the black again, and you start to complete a level. So this game is called LS20. And specifically, with each one of our different games, we do not give instructions. And I was reading a paper from Laura Schultz and Jun Yi earlier, Play, Curiosity, and Cognition, and there was the key concept of curiosity-driven exploration. And that is exactly what we're working on testing here, because without any instructions, you need to go explore around and figure out what to do here. Now let's look at one other game. Beforehand, that was LS20, that was what we call an embodied game, meaning you're controlling a small little agent. In this one, again, you look at it, you're like, I'm not sure what's going on. We start to click around, not much is going on. I'll click green, and then the bar starts to rotate here. We'll keep on clicking, we'll see what happens. Whoops, game over. So that's clearly I'm not doing the right thing here. Let's try this again. Now I'm gonna click the red side, and spoiler alert, I played this game a bunch, and so apologies, but just for presentation purposes, notice how this yellow bar is about to enter into the yellow section there. Once you get the yellow bar in the yellow section, you complete the level. That is what we call a tutorial level. It's meant just to teach the game mechanics, but it quickly ramps up in complexity here. So now the test taker must adapt to this new situation with new rules and figure out what to do for us here. That is 2 demos of the games. Let's take a look at how Frontier AI is currently doing at these games. What we have here is we have a view of GPT-5 high reasoning playing that first game that we showed, which is called LS20. And as you can see, it's taking a bunch of actions, but it's not quite figuring out what to do. And it's not only is it taking a bunch of actions, it seems to be repetitive actions that minimize the amount of exploring and learning that it can do. Now, what we needed to do here is, you'll notice in the bottom left that there's actually an action counter going on. So with every single move that GPT-5 is making, we are counting the number of actions that it's doing. And what we see is that it is making a lot of actions without making a lot of progress. So what we need to do is we need a way to quantify this behavior and how this is going. And we actually took inspiration for this from a paper from some of the people that we'll hear about later today, coming from Josh Tenenbaum's lab, the EMPO paper. And what they did was they created a view of a chart that shows progress as number of actions on the x-axis, and then success in the y-axis for how far you got into a certain game. Now, what's very cool is you can start to compare different test takers as to how efficiently they played a game based off of how much progress they made with how little actions they took. And what this tells us is that your efficiency, as visualized here, isn't just a fun way to look at progress. It's actually a view into how well the test taker is converting information from the environment into the goal itself. So it is learning efficiency, which, going back to Francois's definition of intelligence, your ability to learn new things, it's actually an intelligence efficiency as well. Now, before we get even further on this, I want to jump into some core design principles for ARC-AGI-3. One of the main ones that we have, it might be top line, is going to be we want each one of these games to be easy for humans and hard for AI. The reason why we do this is because humans are our only proof point of general intelligence. And if we can find problems that humans can do and AI cannot do, then that tells us that there is a gap. And as long as we have that gap, we need new ideas and new research to close it. And we will only include a game in ARC-AGI-3 if humans can do it. So while there's a lot of other benchmarks out there that will do PhD++ problems, the hardest problems ever, only a couple people in the world can do them, we are obsessed with problems that humans can do, but AI still has a hard time to do it. But if we're going to claim that it is easy for humans, well, then we need first-party data. And so we actually went and tested a whole bunch of people on all ARC-AGI-3 tasks, and we recruit members of the public, we go and test them, and the important part is that they've never seen these games beforehand, so they're trying them out for the first time. But what's cool is that we're not just testing whether or not they're able to complete each one of these games, we're actually going to be counting the number of actions that it takes them to complete each one of them as well. So as a very brief example on here, we have that same chart we were looking at, but we're about to fill it out with some of the human data that we observed. So in this trial, this is one single human. For them to get to level 2, they spent 10 actions on this certain game. To get to level 3, they spent another 5 actions, and you can start to see how it fills out from here. And then all of a sudden, you get the entire gameplay for how this one single human did it. And what we can do is now we can go and we can fill in the rest of the humans on this. So what's fascinating is that in this view, we get how much action did they need to spend in order to explore? How much action did they need to spend in order to actually execute the strategy that they found? Now, disambiguating between the two is a little tricky, but we're able to see how these two are combined. Now, I'm going to wrap up here very briefly. We've spent the entire, call it 12 minutes now, building up to the next slide about how we're going to be scoring for ARC-AGI-3. So this is the same exact chart that I was just showing beforehand, but what we've done is we've combined all of the data that we get from online playtesters, that we get from AI completing via agents, via our API, and our human testing data. So this is the same view, just with a ton more data. And it may look like a big mess, but we can deduce a lot of really cool information on here. Number one is we can tell how efficient is the average human in playing this certain game. Number two, which is absolutely fascinating to me, is the point all the way on the left-hand side over here. This is what we call the speed run, or this is the best run that we observe. Now, what's interesting about this one is players have done their exploration phase prior to this. So this view right here shows what it takes when you have zero exploration and pure execution. So it's as quickly as you can possibly do it. And when you start to compare the two lines, you can start to ask some really interesting questions, which is either how inefficient is the average human with exploring this game, or how inefficient is the average human with execution on this game. There's one more line, or two more lines I want to put on here. The next one is going to be the best observed first run that we observed from a human. And this means basically who's the best human that we saw, who we can guarantee that it was the first time they saw the game. The delta between the red line and the blue line, that shows you start to back out how much do they need for exploration. And you start to get some really fascinating questions here. Now, where I want to wrap up is there's still an open question as to where does AI fit on this line. And I want to show you, after running an agent competition for 30 days and after testing frontier AI, what we see is that AI, it's currently at the very, very, very bottom. So what this means is that they're spending a ton of actions, but they're not making progress for this. We call this the human AI gap from the ARC-AGI-3 point of view here. And we go as far as to, or let me go back to our original definition of AI. It's problems that humans can do and AI cannot. And this gap shows us a couple things. One is we posit that this means that we do not have AGI right now. And two, this just goes to show how inefficient AI currently is at ARC-AGI-3. This is just data for one game. We'll have data for all 150 games that we're playing on there. And we're going to open source a lot of it for all the public data that we have. To wrap us up here, I'm going to end with a question that we get all the time, which is, what does it mean when somebody completes ARC-AGI-3? And the way I like to answer that question is actually by stating the claims that we'll be able to make once that happens. Number one is this agent will have successfully navigated unknown novel environments on a first time that it has never seen beforehand and the developer has never seen beforehand. It was able to learn the rules of the environment It was able to execute an efficient plan of the game. But most importantly, and this one's the one that is going to blow my mind the most, is getting 100% on ARC-AGI-3 means that you will either have matched or surpassed human-level efficiency at doing all of those things. We get a question, will it be AGI that actually beats ARC-AGI-3? And as with previous versions of ARC-AGI, we do not claim that it is AGI, but we do claim that it is going to be the most authoritative evidence of generalization capability that we have seen to date. My only CTA for you today, two things. Number one is go play the games. That's the most fun part, and that's the way to jump into it. You can do it at 3.arcprize.org over in the lower left there, or you can scan the QR code. And if you're feeling agentic, well, then you can actually go and build agents to try to beat ARC-AGI-3. We would love it. And as a foundation, too, we also have mini grants available for anybody who would want to help us red team ARC-AGI-3. And please come to talk to any of the ARC-AGI-3 members, ARC Prize members after this. Thank you very much.